Good morning, everyone. Can you guys hear me well? Thank you, guys. Okay, as usual, at 11:10, we're going to have our quiz. So stay on the line. If you had any questions before that, please send a message in the chat. Hope my internet is going to work better than on Wednesday today. So Jonathan, ask a question whether we'll stay online after the lecture for questions. Yeah, so the way as normal, the way it works is at the end of the class, I ask if someone wants to ask something one-on-one. And if there are people willing to do it, I will put you in the breakout rooms and talk with each of you individually. So by the end of the class, make sure that you indicate the interest to talk. Sounds good? Okay, thanks. Okay, guys, you should be able to start your tests now. If there are any issues with the test, please send a message in the chat. And good luck, and see you in 15 minutes as usual. So we'll start in a few minutes. I'm just waiting a few more people to finish the test. Okay, in the interest of time, let's start. If most people finished. Okay, so as usual, if at least some of you can turn on your cameras, that would be really and very highly appreciated. Here's our chat. Okay, so let's start. Can you hear me well? Okay, perfect. So we're in week 7. After the reading week, we had a lecture on Wednesday where I talk a lot about how to actually build something real from their, circuits that I show you so far. And we build a big part of the modern CPUs and GPUs, the LU units. So this is what I hope you learn about in this class on Wednesday. So you learn about circuit efficiency, you learn about propagation and contamination delays, and how their circuits can be tested in terms of their efficiency, and that the two different designs might be better in one dimension, but not in other dimensions. So it really depends on which one is better in which case. You need to be careful of that if you actually design a new chip. And we spend a lot of time on building arithmetic logic units. And this is something we're going to spend time today. We're going to look at some of the typical questions that can be asked about LUs so that you guys can practice and I can see how well you understand the material and you can ask questions if you had any. So any questions before we start? Okay, since no questions, let's begin. So the first tryout is multiplication. So remember, we were studying multiplication unit, right? So try to do it by hand and test whether you can properly do the multiplication, right? So I'll give you couple of minutes. So please try it out. And whenever you're ready, please post the answer into the chat. Don't post all the details. I go over the details afterwards. So for people that didn't do it right, can verify and see where they went wrong. Right now, I don't expect you to do any fancy algorithms, so use this great, 3 math for binary. Unless it's not obvious, this is 2 binary numbers that we're multiplying here. And please don't use binary calculators. I know you can do this nicely, but that's not the, the point. Try to do it manually. I'm gonna wait at least someone gonna post the correct answer. So you guys have to do it. You can't just wait for correct answer. Oh, I didn't. Somehow it doesn't show me. There are so many answers here. So for everyone who responded, do you want to convert your number into decimal? So that's the final result will be in decimal. But we see, I think, some correct answers already. Yeah, 130. That's correct. So, yep. Thank you, guys. I don't know why Zoom is not showing me today the chat updates here. Anyway. So this is the intermediate steps, right? You just multiply one by one. So you multiply, this by 0, then you multiply by 1, then you multiply by 0, then by 1, then you add up. And that's what you get, right? Those 10 and 13. This is the number that maps to 130. So anyone has any issues? Like, is it clear? Okay, let's move on. So another question here. The arithmetic unit on the LU looks like this. Remember, there is input logic here. There is this extra input bits, control flow bits. There is input A and B. There's like a parallel adder, right? And this is the operation that we do logically. So the question here is what values for S0, S1, and C in do we need in order to get a subtraction of B from A? So we want to get A minus B, right? So what the values for S0, S1, and C in we need to have? I see one answer and it's not correct. Slightly incorrect. Yeah, so Kevin corrected the answer, but I give everyone a few seconds to think about it, right? So really what it boils down to is this table, right? So remember this table that I showed you before in the class? So if you look at this table, you see by combining different flags for S1 and 0 and how we interpret each parameter, we can get different results. And what we really want is this, right? We want A minus B, because that's minus B, because not is not minus, not plus 1 is minus. So essentially that's subtract. And to achieve that, I need S0 to be 0, S1 to be 1, and Cin to be 1. Okay, so this is how we enforce our adder to do subtraction for us. So we can do increment, decrement, transfer, a lot of other things, and obviously addition. So Terry is asking, why do we want +1? I got these questions on Piazza. I explained it on Piazza. I can repeat once again. Remember, when you do not, you flip all the bits. That doesn't make it minus. It's 1's complement. You need to get 2's complement. So after you flip all the bits, you need to add +1, and that's going to be -x, right? Okay, anyone has similar issue or question? That's like the binary. Like, remember, we covered it several times, but I understand some people might forget. So I got this question on Piazza, I answered so with examples, so it should be clear there, right? Okay, any other questions here for this question? Okay, if there is no question, this is the answer, obviously based on this table. So in another question that you might get, this is all hypothetical questions. In an LU, as 0 and S1 determine which kind of arithmetic or logical function to perform. But there are 3 select signals that go into the LU. So what does the signal S2 does? So essentially, remember this. I'll add everyone to think. Essentially, that's an input into the max, right, that decided which results to go. So if it tells us to take the first parameter, that would act as an arithmetic unit. If it says the second, that is going to act, it's going to take results from the logic unit. Okay, so this is essentially the control unit that selects arithmetic versus logical, right? And this is how it works from high level. You see, from high level, the operations of LU, at least the basic questions, are not that difficult. So I want you to understand how it works. And one thing here, reality is a bit more complicated than what I show you, but this is very, very close to reality, at least on the first chips, right? So you really now understand how the chip is built at its core, because that's the core computational part. Okay. Okay. So any questions about, question 3? Okay. So it's not that difficult, but to make sure that you don't feel like everything is trivial, I'll show you a little bit about the Booth algorithm. Again, I don't expect you to manually do it. It's a very complicated algorithm to work on. It's one of those things I want you to show where computers are better than humans. So like when I always practice with it, I always make mistakes, and computers are very good at it. So let's look at the Booth algorithm. I hope you still remember what's about. Is a way to make essentially utilizing the fact that shift is cheaper than addition, and we can handle special values in a better way by not multiplying by something like 9, but actually utilizing the log sequences of zeros and ones, right? So Booth algorithm is done to do utilize these characteristics in the binary. So this is was reminding you from the lecture material. So here I just summarize it at a very high level. Then each step, I'm going to go deeper into what it does, and then I show you an example, right? And I know it's not going to be that, it's a little bit tricky for humans to follow. So don't be surprised if it looks puzzled for you. So the idea is triggered on the cases where 2 neighboring digits in a paren are different. So essentially, when you had a sequence of bits, when the bits are identical, it's very easy to handle, right? A sequence of zeros, a sequence of ones are easy to handle. So what we really need to worry when we're going from 0 to 1 and from 1 to 0. So essentially, the Booth algorithm trivializes our analysis of the digits. So you only look at 2 consecutive digits. And if they happen to be 0, 1, it means that the multiplicand is added to the result at position I. And if the position is 1, 0, then the multiplicand is subtracted from the result at position I. So the best way to think about it, this is like a sequence of potentially zeros here. So you just need to add something multiplied by this and nothing else. And 1, 0 means there can be potentially multiple ones here. So this is similar to 9, 9. So instead of multiplying to this 9, 9, we add 1 and then subtract. That's essentially what we do. So that's what the Booth algorithm is going to do. So it's going to kind of look at your binary digits, and it's going to sometimes add, sometimes subtract, right? Sometimes it's treating it like, plus x, sometimes minus x, right? And minus x is really like similar to what we showed in the previous slides. It's like this type of notation, right? So instead of doing this, right, it's going to do this, and that's why it's going to subtract, okay? So the result is always the value whose size is the sums of the sizes of the 2 multiplicands. So this is the example we're going to go over. And essentially, I'll just show you where those different cases happens, right? So this is B, this is A. And you see, this is where we see the going from 0 to 1. So remember, when we go from 0 to 1, we would have to add, right, the results of B, right, to that bit. So that's what we're going to do. In the corresponding position, as we're going to go through the algorithm, we're going to add when we see 0, 1. When we see something like 1, 0 in the multiplicand, that means we need to subtract B here, right? So we sometimes add, sometimes subtract, okay? And as we subtract, what we do sign extension, right? So that's what we do. Sign extending this before adding. That's what we always need. So we always, subtraction means sign extension, right? So it's not necessarily easy for us to track, but computer really likes it because it's a very trivial operations. Look at a few bits, right? If it's this, do this. If it's this, do this, right? So that's a very good algorithmically. And then the result. So the challenge is how to make it efficient in hardware, right? There are a couple of challenges here. First of all, if you have hardware set up to compare neighboring bits at every single position, which is what we would as a humans do because it's easy for us, we have a nice way to look at the whole digit, but that's not very good for hardware because this is a lot of hardware. We kind of have that hardware in our brain, so we're very good at parallel operations. But you know, in the real implementation, that's not gonna what we want. So Booth's algorithm is actually trying to avoid a lot of extra hardware. So he doesn't want to have tons of adders in place because we're trying to replace adders with some shifts, right? So this is not like, that's not a good idea to implement Booth this way. Another option is have hardware set up to compare two neighboring bits and have the move done through A, looking for mismatched pairs. So this is what I would, if I want to give you an algorithm that would tell you what to do as a human. The problem is hardware doesn't know what that means. It doesn't know how to move things around and compare. So there's not like a logic, simple logic like that. So it's something that, again, that sounds trivial to you necessarily is mapped into nice, you know, transistors. So we need to still make it to work somehow. So one option is have hardware set up to compare two neighboring bits only in the lowest positions, and then keep rotating the value. So it's essentially, we want to have a logic like only one comparison. So I'm only going to compare two bits in the lowest positions always, right? So I only need a little bit of, and then a shift rotate that, and that we can do efficiently. So this way I don't need to add comparison all across the long value, right, of 32-bit or 64-bit. I only have comparison in the two low bits. And so essentially what you would need to do is, as I said, we would have to shift one bit at a time. And when B is added or subtracted from the correct position, we do corresponding change. Okay. So this is outlines very tediously what you're going to do in the Booth algorithm in using this implementation. Remember, the previous was the conceptual idea. This is the implementation that has to be efficient in the hardware. So you have two multiplicands, A and B, and the result is some product P. We add an extra 0 bit to the rightmost side of A, similarly to how the basic idea works. And then we repeat the following for each original bit in A. So for each bit, if the last two bits are the same, do nothing. So we can easily handle sequences of zeros and ones, right? We don't do any waste, right, on those operations. And why it works, if you had, remember, if you had tons of zeros, it means I really don't need to multiply it, right? The only thing, oh, yeah, there might have been a lag right now. Can you hear me now well? Okay, sorry about that. Yeah, so essentially the idea is when there are tons of zeros in multiplication, they don't do anything. So when I had a long sequence of zeros, I really care about the first one in this sequence. That one would force me to add B to the product, but nothing else is needed. I had a lot of ones and then 0 at the end. It means I need to convert it into all ones minus X. It means I need to subtract, right? That's the whole basic principle. So based on this principle, if the last two bits are 0, 1, I need to add B to the highest bits of P. And if the last two bits of A are 1, 0, then I need to subtract. And we always perform one-digit arithmetic right shift on both P and A. The result in P is the product of A and B. So how would they gonna work in practice? So remember here, things will be shifted to the right, not to the left. So that's not a logical shift, it's like more like a barrel shift. Okay, so that's a very simple example here, multiplying minus 5 by 2. So steps 1, we do, the extension with bits, right? This is minus 5. We add an extra 0 to the right. Then B1 and 2, we need to do sign extension. So we extend it with a ones, and this is the initial product. This is how we set up numbers based on the original experiment. So what do we do next? So we look at the value A, and we look at the last 2 digits. Digits are 1, 0, right? 1, 0 means we need to subtract B from the most significant digits of P. So P is all zeros. So B, right, minus B is this, right? So we need to add that to the results, and this is the intermediate P prime that we get. So this is minus B. We conveniently already collected that on the previous slide. So the arithmetic shift applied after that, 1 bit to the right. So A is shifted, right? So we do rotations of 1. So we get this value and this value for P, okay? So then we keep doing step by step. We see now 1, 1, since digits are both ones, do nothing. We do then arithmetic shift on P and A 1 bit to the right. And that's what happens with these values when we shift them, 1 bit to the right. Okay, keep shifting. So three more times we need to repeat this process. So you see it's very tedious, right? But it's not that complicated at the bottom of it. Then you see 0, 1, it means I need to add. So I treat B as positive number. So I add it up here, right? That's what you're gonna get as a P prime. And then that's my P prime. I need to do another arithmetic shift on P and A 1 bit to the right. So I'm keep shifting, you see. So from this thing, it shifts to this thing, right? Okay. Then next time we get 1, 0. So again, I need to do minus. I'm gonna do minus B, this thing, and that's it, right? And then finally, the final one checks the last, sorry guys, check the last 2 digits of A. We get 1, 1. Since digits are 1, 1, do nothing for P. We just need to do arithmetic shift and 1 bit to the right. And finally, that's P here. And that's our product. I understand that it doesn't look simple at all, right? But from the hardware perspective, that's very simple, right? Because the only thing I do, you see, I compare 2 bits at a time. I never look at more than 2 bits, so I don't need, remember this thing can be 32 bits. So right now, as a human, it looks simple to you, I pick you simple numbers. But imagine that would be 32 or 64-bit numbers, right? That's gonna be a really long number, so good luck multiplying it by hand. But then this is a very easy algorithm. It requires very little hardware. I just need to look at these bits and I need to barrel shift, like I need to shift everything by to the right. And that's pretty much how the Booth algorithm works. I hope you get at least a good perspective and you now understand things that might seem trivial for you to do, might not be trivial for machine and otherwise, right? So it can be vice versa. So that's pretty much it. Yeah, so any questions? So that's everything I have. That's pretty much everything. Again, thanks a lot for a very few people that actually turn on their videos. I hope you guys gonna do it more frequently. Thanks a lot. And I'm here to meet with people who wants to meet one-on-one. So what you need to do now is to send a message in the chat saying I want to meet one-on-one. I will start to put you in the breakout rooms if you had questions. Oh, so Sam asked a question. I'm still slightly confused why you don't do nothing if 1, 1. So very good questions. So I'm surprised nobody asked it before. The idea, Sam, is because there's a long sequence of 1, we're going to eventually handle it. We don't do nothing when we see a pair of that, but when we see the first 0, right, it means that I actually have seen a long sequence of 1, 1, 1, 1, 1, 0. And that's when I do the trick, right? I convert this 1110 into all ones minus that value. And essentially do subtraction. Subtraction compensate for all the ones I've seen before, right? So I don't need to do because I'm delaying my action on ones, all ones. Sam, does it answer your question? Yeah, so it's essentially zeros and ones. Even though we do nothing, we do nothing for two different reasons. Zeros because there's nothing to do, and ones because we're delaying the action. But it's very convenient because for algorithms, it's the same thing. You don't need to do anything when they're similar. So it's like delayed actions, like it's 1, 1, 1, 1, 1, 0, and that's when we act, when we see this 1, 0 at the end. Okay, so then thanks everyone. Yep, thank you guys. And I guess you did very well on quiz today. Hopefully we didn't make it too easy for you. So we'll think about how to make it a little bit more complicated next time. Thank you.